If there is no structure, no pattern in our data, then the models aren't going to pick up on that. Our models aren't going to reveal that. Yes, some models are better than others to reveal patterns, to pick up on patterns, but if there is no structure, no patterns, then guess what? Our model is going to do a poor job with the task we told it to work on. In this situation, let's generate some random points. And we're going ahead and put labels for these points. We'll go ahead and put them on a two-dimensional space. So we have two features for this task. For this problem at hand, we have two features, x1 and x2. And our task is, can we train a classifier that's going to best separate these two classes? And since they were randomly generated, we know our model is going to do a poor job to classify the observation, to separate these two classes. We can visualize it, and sure enough, it's very hard to imagine a machine learning model to pick up any patterns that exist here, to construct a decision boundary that's going to best generalize this behavior. So let's go ahead and take this data, let's dump it to pandas and examine it. Let's go ahead and calculate the correlation. See how well these features are correlated to the labels. So we use the core method of the data frame. Look at how the correlations, and we see very little correlation. So x1, how was it correlated to our labels? Well, pretty much 0, right? 0.3. And then with x2, the labels are also correlated for a small degree. So there is very little correlation. There's little signal here that we're working with. And sometimes that's going to happen. But we can do something about that. We can take our raw data and see what are some good features we can generate with the raw data. What are some new attributes or characteristics I can generate for my observations? This is a bit open-ended task. So sometimes it helps to examine our data, to analyze it, to play around with it, to visualize it, to see if there's any behaviors, any patterns that I can go ahead and construct to add as features for my problem, such that a downstream machine learning model or predictor can get the most from those patterns, get the most from that behavior that we injected into the raw data. This is all the field of feature engineering. As we've seen, our machine learning models, they want data in a structured format, rows and columns. And sometimes the raw data that we're working with, the raw data we collect for the task at hand, isn't in this structured format. And this just means that we have to find a way we can take that raw data and construct it into some structure, rows and columns of numbers, for a downstream machine learning model. For example, if we're trying to do image classifications, then the raw data we have are images. And it's not clear, it's not obvious, at least to me, how we should generate features from those images. One way we can construct features through those images is we flatten out the images. Each pixel is going to correspond to a feature, a characteristic, and the value for that feature is some sort of grayscale value. For example, if we're dealing with grayscale images, we can go ahead and use that to train a classifier to do image classification. But since we flatten out our raw data, we flatten out those images, we're going to lose some spatial behavior, some spatial relationship by flattening out our images and saying that those features are independent of each other, which you understand is not the case when we're working with images. Let's consider text data. Text data is not in a structured format, so we have all these observations, we're going to call documents, let's say sentences. Those sentences are going to vary in length. It's not intuitive, at least it's not obvious to me, how we should go about working with that text data to generate features. Nonetheless, there's some sort of pre-processing, some sort of way we can extract out features from our raw data. Now let's go and look at some temperature data. So we have here. So we have temperature data for different dates, for different cities across the world. And let's go ahead and start analyzing this data. I'm going to run these cells here. So what we're going to do here, what these two functions are set up, is that we're going to plot the autocorrelation for the temperature. Now we'll have some lectures regarding time series, and we'll go into what is autocorrelation. But autocorrelation is a measure of the correlation with a signal with a lagged version of itself. In other words, how well correlated are temperatures today with temperatures in the past? And that's what the autocorrelation plot shows you. This correlation with different lags for our time series. So we have plotted in blue Berlin and Jakarta. Now what do you observe here? The y-axis is the correlation, how well correlated are past values of our time series. What do you observe in this plot? Well, let's first consider Jakarta and Berlin. Now, Berlin's going to have seasons. It's going to have those sort of the traditional 4 seasons. In a place like Jakarta, not so much, or at least not to a great extent, to the same degree as Berlin. So over a course of a year, there's going to be greater temperature variations, greater temperature swings in Berlin as opposed to Jakarta. That's something we know just from our everyday lives. Let's see how it manifests itself in this image here. So what this image is saying here is, let's consider 6. So this represents 6 months into the past. So it says here that there is a negative correlation, a strong negative correlation with today's temperature in Berlin with that of 6 months ago. 6 months ago. That's the effect of seasons in Berlin. But we see in Jakarta, there's a smaller correlation, about 0.25, with the temperature today from 6 months ago. Not a very strong correlation. So when we're working with this temperature data, perhaps one feature we can extract is this measure of autocorrelation for, let's say, a 6-month lag. So we're going to take this raw data, a time series, and generate a feature based upon the autocorrelation at 6 months. Let's do this process. Let's go ahead and do this process for multiple cities and see if there's something we can observe with the results. So we'll do this with this plot here. We'll work with pandas. We'll do some group by operations, apply some of the functions we define up above. And let's go ahead and, with that data, let's go ahead and plot this autocorrelation, this 6-month autocorrelation, as a function of latitude. Take a look at the results. So the y-axis is this autocorrelation. So we see Jakarta right there. So it's about, looks like negative 3.5, which if we look at there, kind of corresponds to that value there. So what behavior do you see with the results? Well, now we see something we can easily visualize, right? We can see something where we can go ahead and let's say our task is to predict this autocorrelation value. We can use something like latitude. We can see this correlation, we see this behavior, this pattern with respect to latitude. In fact, we can look at some of these cities and it kind of makes sense. We see Quito. Quito's near the Ecuador, so it's not going to have much. They're not going to have much seasons, at least not to the same extent as other cities. So we see it has a very small correlation value for 6 months.